Hello guys, this is the exclusive tutorial. So today I'll be taking you guys Physics 101. This is basically for DSU students. The theoretical part of this physics is intermerged, or we can merge it with the university student. The university student can also gain knowledge from this, because this is part of their work. But the calculation aspect, I think they are entirely different. So today I'll be taking you scalars and vector quantities. In my last class, I talked about physical quantity, that they could be classified into fundamental and derived. Then this is another way for classifying physical quantity, either being they are a scalar quantity or they are a vector quantity. So first of all, what are scalar quantities? Scalar quantities, these are quantities that has just magnitude. They are just represented by, they are known for having just only magnitude. Then vector quantities, they are quantities that has both magnitude and they also has a specified direction. So examples of scalar quantities are length. Examples of scalar quantities, scalars, are length. Examples are length, mass. Examples of scalar quantities are length, mass. There are many. In fact, there's no need of writing it. There are many. You have the length, we have the mass, we have the density, we have energy, we have power, many things. They are just, provided they don't have direction. And most of the time, scalar quantities, they are represented, assuming this is length. Length is represented by 5 meters. 5 meters telling you the magnitude and the unit written at the back of it, the unit of measurement for the length. Then when it has to do with vector quantity are usually represented in such a way that they are usually represented by lines, this being the tail and this being the head of the vector. Take note, the magnitude of any vector is determined by the direction, or rather the length of this stuff, the tail is determined by the length of the tail. So if from here to here is 4i, if from here to here is 4i, the 4 here is talking of the magnitude from this point to this point. Then the direction simply is towards the positive part of the x-axis represented by this I. So the direction is this value I, showing you where the thing is following towards the x-axis, but in the positive direction. So that is that for that. That is the way we represent vector. I've already given you the definition for scalar and vector quantity and the way they are being represented. Then positional vector. So assuming this is a vector, the positional vector are vectors that their tails usually coincide with the origin. Their tails coincide with the origin of any vector, and their heads determine the direction which a particle will take. The direction which the particle will take is what determines the head. Then the tails usually coincide with the, how will I call it, with the origin, the fixed coordinate axis of any vector. The fixed coordinate axis of any vector is normally the 0, the origin. So that is that under that. And also in theory, when it comes to three-dimensional states, z, x, y, So this is the vector A first of all. Its direction with the x-axis is this part, A of x. The direction with the y-axis, A of y. And this is the direction with the z-axis, A of z. So normally any vectors, they are usually divided into components, whether it's two-dimensional, whether it's, first of all, whether it's a linear dimensional, whether it just has to do with a line, or when it has to do with two-dimensional plane, the x and the y-axis, and when it has to do with space, when it has to do with space dimension, it has to do with both the x, y, and the z-axis. That is how it's normally, it's when it's fundamental. For this one, this kind of this diagram which I drew here is trying to tell you of a vector that is being represented in space, that has both the x, y, and the z-axis to it. Then what are equivalent vectors? Equivalent vector, any vector is said to be equal if its component elements are also equal. That is to say, if vector A is equal to vector B, then the A of x of vector A, comma the A of y, comma the A of z must be equal to the B of x, B of y, and the B of z. That tells you that our AX is equal to what? Our BX. Our AY is equal to what? Our BY. And our AZ is equal to what? Our BZ. This is an example of an equivalent vector. Then the magnitude of any vector, this tells us the actual value of that vector, or it tells us the actual value of any vector, or it tells us the magnitude of the length of any vector when you are trying to represent it with the vector scale. So the magnitude of any vector, like I said, is the actual value or the scalar value of any vector. So the magnitude of a three-dimensional, or then has to, when it has to do with a two-dimensional vector scale, that is A of x I plus A of y j. This I and our j, remember our I and j is trying to tell you that it is either the vertical component or the horizontal component. The I is trying to tell you is the horizontal component. The j is trying to tell you is the vertical component. The magnitude of this vector, our A, remember I told you it is the scalar part of any vector. The magnitude of any vector is the scalar part. Its length is equal to the length of this value of the total value of this vector. So if we are trying to get the magnitude of this vector, to be equal to ax squared plus ay squared, everything raised to power 1 over 2. That is you trying to apply Pythagoras theorem into this extent. Then when it has to do with a three-dimensional plane, three-dimensional plane, that is a plane that has both the A of x, the A of y, I, j, and the A of z and the k. The magnitude of this kind of vector, remember vectors are represented in this format. In any vector, they are represented in this format. The A representing the vector itself, then the magnitude of the vector itself, then the direction, this arrow at the top of it. So the magnitude of the vector A here is equal to the ax squared plus the ay squared plus the az squared. So this is the magnitude for a three-dimensional vector. Then the other part is addition of vectors. So like as it is written on the board, there are majorly three ways of adding vector, and minus this I will have to introduce one the vectorial method, in fact, the classification of the way you can add a vector, they are enormous. I can also use graphical method to add a vector, but that doesn't derive the fact that you get a definite answer at the end. So polygon method for adding vector, assuming polygon method is, take note, polygon method, they are majorly favorable when it has to do with more than two vectors. When you are trying to add more than two vectors together, then that's when you are expected to add the polygon method in solving for any vector. So assume this vector a1 is one particular vector. The head of this one is linked to the tail of another vector a2. The head of this one linked to the tail of another vector a3. The head of this one a4. This one is a5. Then the last one, being the resultant, is written in this format, such that the tail of the first one such that the tail of the first vector coincides with the tail of the resultant vector. So the resultant vector, the head of the resultant vector coincides with the tail of the first vector, and the head of the resultant vector coincides with the head of our last vector. So I can therefore say that our B, the vector B, is equal to our a1 plus a2 plus a3 plus a4 plus a4, then for this case plus a5. If it's more than that, we can also continue adding. This is when you are trying to determine the vector B, when it has to do with the vector B. In some other cases, they might tell you to know they might not tell you to determine the vector form of this B. They might tell you to determine the magnitude of the B. That is when you now have to. That is when a Unibase scheme will come into. Unibase scheme, where you now have to introduce a format for you to get the angles that circuits this polygon. And if we are to count 1, 2, 3, 4, 5, 6. Okay, this is a 6-sided polygon. You have to now determine the angle our theta, which is equal to 2n bracket 90 minus or rather 90 bracket 2n minus 4 all over 6 times 1, 2, 3, 4, 5, 6. 6 times the angles it will form 1, 2, 3, 4, 5, 6. Okay, or rather divided by 6. Then that is when you now determine the angle. Then you now try and resolve it vectorially to get the resultant vector. But that one has to do with Unibase scheme. But we don't need that now for this. So then the triangular method for adding any two vector. The triangular method for adding any two vector is mostly favorable when it has to just do with just two vectors. The polygon method when it has to do with more than two vectors. Then for the triangular method, the same principle apply, just the same way we did the polygon method. Assuming this is a vector a1, the head of it interrelates with the tail of another. Let's call this one a2. Then the tail of this one touches the head of this one. This is our B. So I told you that the resultant vector, the head of it touches the head of another vector, or rather the head of the last vector, and the tails of it touches the tail of the initial vector. So our resultant vector B is equal to our A1 plus our A2, these two vectors. This is the value for our resultant vector. Then parallelogram method for adding any two vectors. Take note, this is not this method for solving. This is the method for solving the vector form. When it has to do with when you are given angles and you are told to find the resultant. When you are given angle and you are told to find the resultant, then we can apply our normal cosine rule. Our normal cosine rule, the formula for it is A1 square plus A1 square plus A2 square minus 2A1 A2 cos theta. Remember, this is square root. We are trying to determine the magnitude. This cosine rule, if you are really familiar with your normal SS1 cosine rule mathematics, then you can definitely remember this formula. Or we can also use our sine rule. This part being our theta, maybe here being our alpha, the other part being our beta. But when we go deeper, we'll understand this more. So then parallelogram method for vectorial addition of any vector. Parallelogram method states that if two vectors they are being represented at the adjacent side of a parallelogram, say if you add them together, their resultant will definitely be the diagonal of that parallelogram. So assume this is a parallelogram. Remember, I said from what I've seen so far, I noticed that all the techniques for adding any vectors, they interrelate with each other. The head to head and the tail to tail for the resultant. You can use it to gratify any of these vector methods. So let's assume this is the resultant being the diagonal of this parallelogram. So first of all, you have to short circuit this part. So according to the normal law of parallelogram, it says that, let's assume here is O, here is A, here is B, here is C. Our OB vector OB is equal to, or let's just give it a particular vector. Let's call here A1, A2, and here our B. Okay, so our OA, the vector OA from O to A plus our AB will give you the vector OB. If you want to do some estimation on this part, you will notice that it moves from our O to A, then from our A then to A, then from our A to B. You can just remove these two A's, then you'll be left with OB, giving you the vector here, the resultant. So it moved from O to A, then from A to B. So our normal law of parallelogram says, let's not leave that fact. Our normal law of parallelogram says that the adjacent side of any two parallelogram, the adjacent side being this part, our OA and our OB, the resultant of it is usually the diagonal. This is the diagonal of any vector. That is our parallelogram rule. So assuming these two vectors, they are inclined at an angle, and here is our alpha, here is our beta. So we're told to find the resultant, and our resultant is the magnitude of this vector b. The magnitude. At that point, we'll be using our cosine rule as usual, which is a1 squared plus a2 squared minus 2a1 a2 cos theta, the square root. Or using the cosine rule for this one, cosine rule. Or you can use your sine rule, which is our a2 over sine alpha is, remember this is the magnitude of the vector now, is equal to our a1 over sine beta, and is also equal to our b over sine theta. So this is that under the parallelogram method for adding vector. So the next one is the vectorial method. The vectorial method is very simple. Assuming this is a vector A, it has axi ayj plus azk, and this is our b vector. Our b has bxi plus byj plus bzk. So if you are trying to add it vectorially, the component x will be added to the component s. So our vector A plus our vector B will be equal to our ax plus bx, or in vector I, plus ay plus by, or in vector j, and plus our az plus our bz, or in vector k. This is how we add any vector vectorially. So then, just like I drew that diagram on parallelogram method for adding any vector and the triangular method, I can also show you a method for representing the triangular method for subtraction of vector. If you want to subtract any two vector you want to represent it using the triangular method, then you are going to draw two vectors. First of all, these two vectors, their tails are touching each other. Then the tail of one is touching the head of another. So let's assume this is a1, a2, and this is our b. Take note, I said the head to head determines our resultant vector. This one touches the head of this and the head of this. Then this one touches the tail of this, the tail of this. Therefore, our a1 is the resultant vector here. So our a1 is equal to our a2 plus our b. How can I get my vector b? My vector b is therefore equal to what? a1 minus a2. Remember, all these are vectors. So that is that under subtraction of vector. Then the multiplication of vector. Anytime you are multiplying a vector by a constant value, if you are trying to multiply any vector by a constant value, the value of that vector changes entirely. So this is a vector A, and I'm multiplying it by a constant c. C can be anything, 22/7, can be anything, pi, can be 40, anything. They are just constant. They don't have any units. So let's assume I'm using my constant c to multiply this vector. I'm trying to use a constant c to multiply the vector. So if I'm multiplying it, it will now give me CA. This automatically has changed the nature of this vector. And maybe if you want to represent it to be CAXI plus CAYJ plus CAZK. So this one doesn't matter. The multiplication of any vector changes it entirely. If after multiplying it by a constant, it becomes the reverse, that it turns reverse if it has a negative sign. And if after multiplying it by a constant, the value equals 0, that vector has automatically become a non-vector. Then, what are the laws of vectors algebra? There are certain laws which vectors interrelate with, or rather, which they adhere to. Some vectors are mostly they are commutative, distributive, and associative. Vectors are commutative, distributive, and associative. Anytime you are solving any vector, take note they are always commutative, associative, and distributive. So assuming this is a 3 vector A, B, and C, then we're given a constant M and N. Constant, like I said, they are just normal values. They can be 22/7, they can be 240, pick any number. They are the constant. So A plus B, or rather MA plus A plus B commutative is equal to B plus A. This is a example of a commutative law, that is an additional commutative law. Then in multiplication commutative law, BA is equal to what? AB. And if you are introducing M into it, our MA is equal to what? Our AM. This tells you that any vector, all these things are vectors. This tells you that vector is definitely commutative. Then distributive, vector A plus vector B plus vector C. You are adding these 3 vectors to show that it is commutative, it is associative. Our A plus B, adding it together, then add it again to your C, it will give you our A plus B plus C. Adding these 2 together separately, then adding it to your A. That tells you that any vector is definitely associative. You can test this by implying any value for a vector. You can just pick 2i plus 2j, then pick your b, I plus 1 plus 2. You can just do that, and if you test it, definitely you must have, if you adhere to this law, if you are trying to use it, you must definitely get a value that are equal to each other. Then aside that, vectors are also distributive. This will tell you that our M vector A is plus M vector B. So I'm not trying to multiply the constant by a 2 vectors. So it is distributive in the sense that if you multiply this one by this one, multiply this one by this one, this value will give you this value. You are trying to distribute M to vector A and B. And remember, I told you that the multiplication of any vector by a constant changes the vector entirely. And the last part is resolution of vectors. How do we resolve vectors? So the word resolution means you trying to consider the effect of the resultant, or rather the major vector, in its coordinate axis. First of all, I said the definition for resolution of vector. If you are trying to resolve a vector, you are trying to take the effect of the resultant or the magnitude of the resultant to its coordinate axis, that is its coordinate. If you are trying to take the effect of the resultant to its coordinate, that is referred to as resolution. So this coordinate order here is called the horizontal coordinate, and normally A of x is equal to A cos theta. How did I get this? First of all, you plane out your triangle. This is your angle theta. This is the resultant, like I said, A, and this is our A of x. These 2 points are just our point of focus for this part of it. So since these 2 points are our point of focus, our cos theta is equal to adjacent A of x all over the hypotenuse A. So if you cross multiply, definitely you'll be having your A of x value to be A cos theta. That is how they did this. And if you repeat this same principle I applied here to this A of y, making here to be the value for our A of y, you get our A of y value to be equal to A sine theta. So that is that under the resolution of vectors. Then for three-dimensional plane, so for three-dimensional plane, when it has to do with the z, y, and the x axis, take note, a three-dimensional plane, that is the space plane, they are usually mutually perpendicular to each other. When I mean mutually perpendicular to each other, I'm trying to tell you that such a plane, the angle between each of its coordinate axis, the x, z, and y dimension, they are all at 90 degrees to each other. Take note, these are our x coordinates, z coordinates, and your k coordinates. So the general equation, like the unit vector for this three-dimensional space plane, is usually written in this format. So the unit vector for this format is written in this format for a three-dimensional form. Take note, our A of x all over the magnitude of A, this constant is usually equal to the cosine direction of the vector here. The vector is the A. So the cosine direction here is the cosine alpha. This A of y all over the magnitude of A is equal to cos beta, our cos beta, and our A of z all over the magnitude of A, this is the vector, is equal to cos gamma. So this one tells you the cosine direction. The angle alpha, beta, and gamma, they are referred to as the directional vector, the angle of the directional vector of the vector A there. So that is that under the unit vector aspect for the three-dimensional. Take note, there exists some other forms of vectors that are referred to the unit vector. Vectors, unit vector, first of all, they have their magnitude equal to 1. That is to say, if I take this one, the magnitude of this whole scale, it will give me 1 at the end. Magnitude, I told you now, A of x squared plus A of y squared. Like I said, this is a unit vector, and A of z squared is equal to the magnitude of the vector A. So if I'm trying to get the magnitude of this vector, I will just take the square of this one, the square of this guy, take the square of this guy, and this guy. If I take that, I'm going to get the magnitude of this vector. So a unit vector, their magnitude is definitely equal to 1. At the end of it, get the magnitude for this vector, it will give you 1. So there exists some other form of vectors. They are called normally the normal way which we use in symbolizing a unit vector is this format. Is either we use our mu in capacity, or we use or we use our e. Okay, the e is in this format. So is either we use mu, u, or e. So there is the basic vectors themselves. They are just vectors, unit vector that are only aligned towards the coordinate axis. Maybe it's just a unit vector in the sense that its magnitude is just focused definitely on just the x-axis, or just the y-axis, or on just the z-axis. I can write them in this format. U of x is equal to 1, 0, 0. This is a 3-vector scale, but its x-axis is just the one having a magnitude, the remaining one has 0. Same goes with the y. Same goes with the y, 0, 1, 0. And same goes with the z, 0, 0, 1. So that is that under that part. I call these vectors basic vectors.